to introduce Bhavik Mehta, who will be talking about formalizing modern combinatorics.
Thank you very much, Larry, and thank you for the organizers for having me. Yes, I will be talking about formalizing modern combinatorics. I'll talk about some of my work in this direction. I'll pick some of, as opposed to some other talks you might have seen earlier in the week about formalization, instead of talking about one project, I'll talk about a couple of projects, picked in a very biased sense of projects that I have worked on, that I have liked, and projects which have some emotional connection to Cambridge for me, because we're here. In general, lean formalizations and formalizations in general can take quite a lot of time to finish. I think this is not a surprising claim to anyone. We talked about this frown factor earlier. There was also a big factor of the time it takes for finding a proof compared to formalizing a proof can be pretty massive. Much of the effort in MATLib and in the AFP and in other formalized libraries is to formalize classical and well-known results. And when I came to the community, there was lots of this happening. And I wanted to see if we could use these tools to formalize more modern things, to try and do things which are actually happening and actually getting talked about in mathematics departments. And this was happening in the community, but not as much as I wanted. So I tried to make a deliberate effort to find things which are exciting in mathematics and try to formalize those. In particular, in certain cases, the formalization can be finished quite soon after the theorem has been proved or made public or something like that. So I'm going to show you a few of these examples. For each one, I'll give you some idea of the math of the problem. I won't go into all the details. I'll talk about the story of the formalization, trying to give you some idea of how it came about, and in some cases talk about what made the formalization particularly easy or particularly difficult. So the first one, this is the oldest example I have. This is from late 2021. Thomas Bloom proved that if a set of naturals has positive density, if you don't know what that means, that's fine, but the rough idea is that the density measures how much of the natural numbers the set takes up. So the even numbers have density of half, the multiples of 3 have a density of a third, and the prime numbers have a density of 0. So if a set has positive density, then it contains a finite subset S whose sum of reciprocals is equal to 1. And then by June 2022, we had formally verified it in Lean. There's a reference to the paper at the bottom, which you might not be able to see. Oh yeah, but this QR code here, which will be there for the whole thing, you can scan that, you can get access to the slides, and you can click on all the links and stuff like that. The informal proof for comparison was published in GEMS in July 2024. So you have some idea of the time between the proof being found, the proof being formalized, and the proof being published. On a more personal note here, I first met Thomas Bloom in Cambridge when I was doing part 3. He taught me for analytic number theory. Then I got into Lean, and a couple of years later, he proved this result. And maybe a day or two after he proved this result, he went on Twitter, as it was at the time, and asked how much analytic number theory is in Lean. A reply to that was posted by Alex Santorovich, saying, "Are you interested in formalizing your new result?" And Thomas Bloom replied, "Maybe." So I sent him an email. And that's how this project got started. This has a number of different significant impacts. This was an open problem of Erdős and Graham, sometimes called the Erdős-Graham problem. A weaker form of the result, something easier, was proved in 2000 and was published in the Annals of Maths. So an easier form of the thing was significant enough to be in the Annals of Maths. I should say that the new proof uses many of the ideas of the old one, so it's not a significantly, all of the ideas are not brand new. It does depend on the ideas present in the earlier one. But the earlier one was still, on its own, very significant. At the time, this was the first recent analytic number theory result to be formally verified. There are more recent interesting examples, but at the time, this was the first. It was also the first formalized instance of the Hardy-Littlewood circle method. It was also the first formalized solution to a long-standing problem of Erdős. On Monday, we saw the Erdős problems website and how DeepMind is formalizing some of the statements of these. At the time, the website didn't exist, but the first formalized solution to one of the long-standing ones was this project. And also, that website is made by Thomas Bloom, so there's another connection here. As part of this project, we proved a number of things, some basic analytic number theory results. This is the divisor bound. This is saying that sigma 0 will be the number of divisors of n. And this is saying that for every positive epsilon for sufficiently large n, the number of divisors bounded by n to the epsilon. The reason I highlight this one, this has since been done in other languages and in other places. But this one was something we used for the project, and which I directly learned during my Part 3 class by Thomas Blue. So I used my lecture notes from his course as part of this formalization. As a consequence of this, we proved this theorem of Wigert. This particular one wasn't directly useful for the formalization, but I think it's a nice result. In lots of analytic number theory textbooks, this is stated as needing the prime number theorem to be proved, but it turns out it doesn't. There are some textbooks which do correctly say you can do this without the prime number theorem, and that's what we did here. And you can see a fairly clear matching between the informal and formal statements. So it's the lim sup of this log of the divisor function times log n. Over log n, the lim sup of this quantity is equal to log 2. Okay, so those are some of the things we used along the way. And then our main result is this upper density claim. So I won't read it out. Hopefully it's fairly clear for everyone, including the people who aren't familiar with lean, that this corresponds to what I said it does. But that said, there are some things we should make sure of. The upper density. This is not a thing in MathLib yet, and it's something we defined as part of the project. I could have defined the upper density of a set to be 0. I didn't. I promise you I didn't, but I could have. And if I did, all of this work would have been for nothing. So when a theorem like this is formalized, it is important to check the definitions. And this is all public, and you can check that I did what I said I did. The other things I did to convince myself is that I proved the upper density of the entire natural numbers is equal to 1. I proved the things I said earlier about the upper density of the evens and of the multiples of 3, or a half and a third respectively. So these are things which I think is good practice to check as part of a formalization to make sure that you're doing what you said you've done. Another important thing here is this coercion to Q. In lean, if you write 1 over 2 or 1 over 3, then it will by default assume that everything is a natural number. In particular, the output is a natural number. Well, how is 1 over 3 a natural number? Lean will round down. And so it will be 0, and so this theorem will not be very interesting. In particular, it will be true only if S contains 1, or is exactly 1. Okay, I can't go back for some reason. There we go. It will only be interesting when S does or doesn't contain 1. So the meaning of the theorem is quite different. So this is another thing which should be checked. Let me talk about some of the more technical aspects of the proof. As most formalizations these days go through, we went through the blueprint process. Here was the first step of that. This is one of the key propositions. This is kind of the main technical proposition which drives the thing. I won't read the whole thing out, but you can see it's not the simplest thing to understand. It's a long proposition, and it was one proof which was 3 pages long. The first step of the formalization process was to turn it into the blueprint, which in this case turned out to be a few paragraphs of detailed proof, along with about 20 earlier lemmas. So it got split up into a bunch of earlier lemmas. Each one had 1 to 2 paragraphs of proof, and then this main one had a couple of paragraphs of proof as well. So there is this first expansion factor. And then there's the second expansion factor. This is going from the informal blueprint into the formal version. And so this ended up, for only this statement, not including the earlier lemmas, it was 80 lines. And the 20 earlier lemmas turned out into 100 earlier lemmas instead. And this is actually the one which uses the circle method. So this is the same lemma who, inside the proof, uses the circle method itself. Here's one of the things, or here are 2 of the things, actually, which we had to prove. For all C, and for all sufficiently large n, that first inequality, 1 over log n plus some horrible stuff, is less than or equal to some other horrible stuff. And then the second one's even more horrible. These were things which we had to prove. In Isabella, I understand there is a real asymptactic, which makes this very easy, I believe thanks to you. In lean, we don't have this. So this had to be proved essentially by hand. This was pretty miserable. This was one of the more painful parts of the formalization. And also these kept showing up. We ended up giving them some slightly silly names by the end of it. But let me switch tacks now. So I want to talk about a second project. This is a much smaller project. It's a little bit cuter, a little bit more self-contained. This is the resolution of what was called the Fishbone conjecture. Okay, so what's the Fishbone conjecture? First, I need to give you a little bit of order theory. Let's say we have a partially ordered set P. Hopefully most people knows what this means. It's a set with a relation which is reflexive, transitive, and antisymmetric. A subset of this partial order will be a chain if for any 2 elements they are comparable. This is a reasonably well-known definition, but I wanted to write it down just to remind you. This appears in stuff like Zorn's lemma and stuff like that. And then the second definition I have here is that of an anti-chain, which is essentially the opposite. It's that for any two elements of A, if they are different, then one is not less than weakly less than the other. This is less common of a definition than a chain, but it still shows up. For example, this shows up quite a bit in the Carlson project. You study anti-chains in section 2 and section 6, if I remember correctly. So this is less well known, but does appear in mathematics. But what's the Fishbone conjecture? Well, first I want to give you two examples of posets to try and make this a little bit more concrete. So my underlying set will be pairs of natural numbers times the natural numbers. And what's the relation going to be? It's going to be that one pair is less than the other if the first pairs are less in that relation and the second pairs are as well. One way to think about this partial order is if I have 3 apples and 5 oranges and you have 4 apples and 7 oranges, you have more than me. But if I have 3 apples and 5 oranges and you have 4 apples and 1 orange, it's not clear whether you have more than me. And what's the price of apples and oranges today? So in this partial order, you can only make a comparison if it's a genuine improvement in both coordinates. Visually, you can view this as going up and to the right. So here is a picture of natural numbers times natural numbers, and the relation will be, well, if one thing is here, then that is bigger because I've gone up and to the right, or maybe this will be bigger because it doesn't have to be strictly up, but this will be incomparable. So what does a chain or an anti-chain look like in this picture? Well, there's a chain. Every part is going up and to the right, essentially. And then what does an anti-chain look like? Well, broadly the opposite. It's going down and to the right, or up and to the left, if you like. So I've drawn anti-chains with dotted lines and chains in straight lines. So here are some examples of chains and anti-chains. Okay, let's now take a... Oh, that's an important point. So in this picture, all anti-chains are finite. This is not completely trivial to prove. It's not so bad by induction or by Dixon's lemma, if you know what that is. But it's also so hopefully not too hard to convince yourself that in here, all anti-chains will be finite because you have to go left, and as you keep going left, you kind of will get stuck at some point. So in this picture, all anti-chains are finite, but there are almost certainly infinite chains. For example, the entire x-axis will be an infinite chain. Okay, let's look at a second example. Here I'm going to take the same set, but restrict it a bit. I'll kind of cut out a diagonal. And in this case, my relation will just be go up. You're not allowed to go right anymore, you can only go up for comparability. So here is the set, or here's a picture of the set in question, and here are some chains. All you can do is go up, your chains are just vertical lines. And here's an anti-chain, and there are many more anti-chains in this picture, but the idea is that you can't have any two things in the same vertical column. Okay, now here, there will be infinite anti-chains. This time the entire x-axis is an infinite anti-chain, but now all chains are finite. So we've had this difference in properties. What's the Fishbone conjecture now? The actual name of it is the Aharoni-Korman conjecture. It's also been called the Fishbone conjecture, and I'll call it that because I think it's a more fun name. This conjecture says that any partially ordered set has either an infinite anti-chain, we've seen some of those already, or the second condition, which is a little bit more technical, but let's go through it. A chain, together with a partition of the entire poset, into anti-chains, so that our specific chain C has an intersection with each of the anti-chains. So we'll partition the entire thing into anti-chains, and find a chain which touches each of those. It doesn't have to touch every anti-chain, but it has to touch every anti-chain in our partition. Okay, and the conjecture says that at least one of these will be true. This was an open problem for around 40 years, and every partially ordered set you can basically think of, and everyone did think of for 40 years, did satisfy the conjecture. Let's confirm that with the first example we had. Because we saw that all anti-chains were finite here, we can't have the first alternative, so we must have the second. And in red, I've drawn the chain we're looking for, and in the dotted lines, I have given you an indication of what the partition will be. So we partition in these diagonals. This chain will meet all of them, and also this is a partition of the entire space. Okay, so we have verified the Fishbone conjecture is true for this example. But in late November 2024, Lawrence Holland found a counterexample. This is the construction of the counterexample. He calls it P5. It's defined on this triple, and it is this short but not entirely clear construction. I won't go through all the details of it, but you can see it's relatively explicit, but it's not completely obvious why this works or what properties this thing should have, or anything like that. Now, the reason I found out about this, I was on YouTube trying to fall asleep, and I got a recommended video, which is a popular maths video called "The Fishbone Conjecture Has Been Deboned." So I watched this video. I saw these pictures. I took these pictures from the YouTube video. Oh, sorry. I replicated the pictures from the YouTube video, and I thought, hey, this is an interesting counterexample. I wonder how bad it is to formalize. And then as I kept watching the video, the creator of the video mentioned the author, Lawrence Holm, and I realized I recognized the name because I met him here in Cambridge. We turned out to be Facebook friends already. So I started formalizing this, but there were some gaps. And when you formalize something which has been proved by alive authors, as I have the privilege of doing, I can just send them a Facebook message and say, hey, look, I can't understand this bit of the proof. I thought there was a gap. I'm not going to say that to him. I said, I don't understand it. And he confirmed that, yes, there was a gap, and we filled it in together. So we fixed the proof, and then we finished the formalization. So this was about, by mid-January, the thing was finished. But there's an important point to this, which is that large parts of the corrected proof were only found after the formalization started, and arguably because of the formalization.
Was it the same example? You have to change the example.
Yes, the same example, but a different proof. So essentially, the main workhorse of the proof, there was some part which didn't quite work, and so we modified it to make it work. But it's the same construction. And let me move on to the next example. So this is, I think, the biggest one in terms of the number of lines of code so far, and other things I'll talk about. This is a theorem which I really like. This is from Ramsey theory. So we've kind of skipped between order theory, combinatorics, analytic number theory. These things, they have some aesthetic similarities, but what I wanted to give you is an idea of different things which I've worked on. So let me set up the problem. We're going to fix natural numbers k and l, and I'm going to take a complete graph on n vertices. I'm going to color each of its edges either red or blue. A red clique will be a subset of the vertices where all of the edges between them are red, and a blue clique will be where all of the edges between them are blue. One question you could ask is, does every coloring have a red clique of size k? Let me say n is quite big, k is maybe 10. Does every coloring have a red clique of size k? Well, obviously no. I could just make everything blue. And there's obviously no red clique. I could ask the opposite question. Does every coloring have a blue clique of size L? Again, obviously not. I could just make everything red. What about if I only ask for one of these two? So if n is large enough, it turns out that every coloring has either a red K clique or a blue L clique. This was proved by Frank Ramsey in the 1920s. He was originally doing this for logic, but it's turned out to be a hugely influential theorem in combinatorics. And now there is just a field called Ramsey theory essentially based off this theorem. Because of this theorem, I can then make this definition. I could define the Ramsey number of k and l to be the smallest n, such that every red-blue coloring of the complete graph on n vertices has either a red clique or a blue clique. So we know this exists by Ramsey's theorem, as I mentioned on the previous slide, and so I could just ask for what's the smallest one. But let me try and make this more concrete by giving you some examples. So what I will give you is a pictorial proof that the Ramsey number 3 is equal to 6. To show it's equal to 6, I will first show that it's strictly more than 5, and that it's less than or equal to 6. And therefore, I prove it's equal to 6. Okay, well, to show that it's more than 5, I need to give you a graph on 5 vertices and a coloring of all of its edges, which doesn't have a red 3 clique or a blue 3 clique. Or what's a 3 clique? It's just a triangle. So I need to give you a coloring which doesn't have a red triangle and doesn't have a blue triangle. And hopefully it's fairly clear that that is one. There is no blue triangle of edges and there's no red triangle of edges. So that's your proof. R33 is more than 5. Okay, R33 is less than or equal to 6. This one's a little bit more subtle. In particular, because I have to say that for every coloring, I must be able to find one of these triangles. Okay, so right now I've put all these things in light gray because I haven't colored them in yet. But if I do have a coloring, then I know that, let me just pick the top vertex. The top vertex will have 5 outgoing edges, and they will be red or blue in some order. but I can guarantee that there will be at least 3 edges of the same color going out. I don't quite know which color, but it must be one of the colors. Okay, so I've done it in pink. I hope the color's clear. It looks a bit red. This is meant to be an ambiguous color. You could, without loss of generality, say it's red. But I've drawn it in this kind of purplish color here. Okay, so let's say that these 3 are all the same color. What I want to do now is consider this black triangle at the bottom. I've drawn it in black because, again, we don't know what these colors are. But let's think about them. If any one of those is in this purple color, then I have found a purple triangle. And purple was either red or blue, so I found the triangle I need. So if any one of these black ones is purple, then we have the thing we want. Otherwise, none of them are purple, which means they must all be the other color, and therefore that's the triangle we want. So in either case, I can find the triangle out of an arbitrary coloring. Okay, great. So that gives me the proof that R33 is equal to 6. Determining these Ramsey numbers is a notoriously hard problem. We have the answer for R33, we have the answer for R44, we don't have the answer for R55. Recently, the bounds on it were improved, so we know it's between 43 and 46, but we don't know anything better than that. And there are some famous stories about Erdős and aliens that you could look up about this, which maybe some people have heard. If you haven't, you can look it up. It's kind of a fun read. But if you're doing mathematics and you can't work something out for concrete values, you can ask what happens for arbitrarily large values instead and try to get some bounds on that. So that's what we'll do. So Ramsey in 1928 showed that this number is finite. That doesn't give you many bounds at all. Let's try and look for some better ones. Erdős and Szekeres in 1935 gave some slightly stronger bounds. They said that the Ramsey number of k and L is less than or equal to k plus L, choose L. And in particular, this diagonal Ramsey number, which is when we set k and L to be equal, which is one of the more commonly studied cases, we have an upper bound of 4 to the k over square root of k. You can essentially show this from the earlier part and some Stirling approximation or something like this. What's important, though, is that there is this 4 to the k and some polynomial-ish denominator. And this is important because Thomason in 1987 improved the bound. He improved this polynomial thing in the denominator. He proved it from 4 to the k over root k to 4 to the k over k. It's better. And this was also fairly significant, but we still have this number 4. This pesky number 4 is still there. And you could also write this as 4 to the k minus c log k, which I will do. Conlon in 2009 and Saar in 2020 improved the bound more. They got an upper bound of 4 to the k minus c log k squared. This is an improvement. It's a slight improvement, and we still have this 4, but it's a significant improvement. Conlon won some prize for this, I should know, but I can't remember what it is. So this was also a fairly significant result. Again, on a personal note, when I was studying graph theory here in Cambridge, in a building over there somewhere, I was learning about Ramsey's theorem. And I think the first 3 of these bounds were presented. And the lecturer explicitly wrote, it's an open problem to determine whether RKK is big O of 3.999999999 to the k. 10 nines. At the time, that was an open problem. So that's a tiny improvement, but I think it illustrates that getting this 4 any smaller was an interesting and difficult problem that many people had tried and no one had succeeded on. But how small could we make it? You should ask for lower bounds at this point. Erdős proved this lower bound of root 2 to the k. This is often called the first instance of the probabilistic method, which is this idea in combinatorics where if you want to construct something, you construct it randomly. And in this case, if you just pick a random coloring, it probably works. That's the proof idea of this last part. Just color everything randomly and it will probably work. But we don't really have anything better than this. The lower bound was improved by some factors, but you still had this root 2. And so if I try to extract this number by taking this kth root and then the limit, we have a lower bound of root 2, and we have an upper bound of 4. And we don't know where in between it is. In fact, we don't even know that the limit exists. We don't even know that this limit exists. That's why I've written this limit fin lim sub. There are different guesses as to where it was, or where it should be. But we don't know that the number exists, and if it does exist, we don't know where it should be. That was up until 2023, when this result was made public. This one This was announced in 3 places around the world simultaneously, one of which was here in Cambridge. And the seminar in the Cambridge Combinatorics seminar where they announced it was often called, people said it had the feeling when Wiles made his famous announcement. Apparently the vibe before the seminar was similar to that one, supposedly. So this had some fairly significant impact. The paper's around 57 pages long, the proof is about 50 pages long. It took the authors about 5 years to find and check this. That gives you, it's a difficult problem. So I heard about this, I heard about the seminar, I had some friends who went. Then I defined Ramsey numbers, and then I formalized the proof. In particular, I formalized the proof in 5 months. Ended up finishing 5.5 months after the announcement, but I took 2 weeks to get started. So I formalized the whole thing in about 5 months. That's true. And this one is still in the referee process.
Oh, is that an explicit epsilon here, or
In that particular statement, it is not explicit, but if I change this k to a for all sufficiently large k, then we can make it explicit. So you have this trade-off of, do you want it to be for all k or for all sufficiently large k? Sufficiently large k is probably the interesting one, and in that case, their proof gives you something explicit, and therefore mine does as well. Let me give you a rough idea of how this proof works. I don't want to go into too much detail on this, but first I'll describe the proof that Erdo Scheckers had back in the 30s. So this is the proof that the Ramsey number of KL is less than or equal to 2 to the k plus L. Well, let's say here's my graph. I'll put all of my vertices in this big blob X, and I'm just going to pick one vertex, just an arbitrary one. It's got some edges coming out, some of them will be red, some of them will be blue, and I'll call this special one V. What I would like to do then is look at the number of outgoing edges. I've got some red and some blue, and I'm going to pick the color which is more popular. So the color which appears more than half the time, it's got to be one of them. Let's say it's red without loss of generality, so I don't have to mess around with purple again. Let's say it's red, and in that case, I will move V into this red block A. So I've got this red blob at the top A, and I've got the blue blob at the bottom blue blob at the bottom B. And because this one had more red edges going out, I will move it into the red side. What I will do then is delete all of the vertices which were connected to V by a blue edge. So because I moved it into the red one, I have to delete all the blue outgoing edges. And similarly, if I moved it into the blue side, I would have to delete all of the red outgoing edges. Okay, let's consider what happens to the size of this set X whenever I make this procedure. Well, the color I picked was the one which was most popular, which is about at least half the size. So what that means is the number of things I delete is roughly less than a half. Maybe plus or minus 1, but asymptotically we'll say it's less than a half. So in each step of this process, the size of X goes down by, at worst, a half. Yeah, there's a good chance it goes down by less than that, but at worst it will get halved in size. There's another thing which happens during this process, is that I have these invariants which I've maintained. I started off with A and B being empty, but as I keep doing this process, we have the invariant that every vertex in A is connected to any other vertex in A only by a red edge. And every vertex in A is only connected to things in X by red edges. So that's what I have this red thing here to indicate, that everything inside is red and everything going from here, or between these two, is also all red. And similarly for B, everything inside B is all blue with each other, and everything in B to X is also all blue with each other. So these are properties maintained as invariants over time. Well, what does this mean? If I'm going for a contradiction, and I say that the graph doesn't have any red K clique or blue L clique, then the size of A, because it's always a red clique, it must remain below size K the whole time. And the size of B must remain below size L the whole time. And so as I do this process, I can't do it more than K plus L times. Otherwise I would have a contradiction. But as long as the size of X is at least 1 or something, then I can always take a vertex out and iterate the process. So I can only take K plus L, less than K plus L steps, but as long as the size of X is more than 2 to the K plus L, I can take another step. Therefore, the initial size of X has to have been less than or equal to 2 to the K plus L, which gives us the bound we needed. I did hand wave a bit here when I was deleting by a half, but if you do the calculation more carefully, it does work out. So yeah, but at each step, the size of X shrinks by at most a half, so it kind of started being bigger than 2 to the K plus L. I mentioned the hand waving. The slightly more typical way of doing this proof is doing induction on k plus L, but I want to indicate it like this because it's closest to the proof I'm about to show you. And the proof I'm about to show you uses this concept of a book. What's a book? Well, it's kind of what I indicated earlier. It's this A, which is connected to something else only by red edges. That's called a red book. And B is also going to form a blue book. Or rather, blue in relation to X will be a blue. We're going to modify the algorithm as part of this proof in a fairly complex way. I won't go through all of the details, but what I want to indicate to you is that it's the same idea of argument, just with a bunch of the details changed. So we're going to move these vertices in the same kind of way, while searching for a red book as well as searching for A and B simultaneously. Throughout this process, we have to control certain quantities. We have to make sure that the red density between X and Y doesn't get too small. And I've sketched the different steps we're going to take before we take a red step or a blue step. Now we're going to have 4 different types of steps, which will have different properties. And our stopping condition, instead of X being size 1, will be X being less than another Ramsey number. I won't go through the details of these steps, but if you've done some formalization before, there should be one thing standing out to you from this slide. Any guesses? Or maybe there's multiple things standing out to you from this slide. There's one thing which stood out to me. Any guesses?
Rational numbers, fractions to calculate with.
There's fractions to calculate with. Is this a rational number?
Indeed.
Most likely it's not a rational number. And in the paper, this is what they wrote down, and with no comment about it. We've defined this well-known quantity for natural numbers, and suddenly I'm plugging this arbitrary real number into it. It's computable, but it's a real number. So this is the sort of thing which often happens in combinatorics, where when everything is arbitrarily large, we just often pretend things are integers. How do you fix this? There are multiple ways. You could round, you could take floor, you could take ceiling, you could add error terms. What I ended up doing was going through the proof and checking that it made sense, or at least convincing myself that it made sense if I put a ceiling here. And I was prepared to change to a floor later. I just, it looked like ceiling should work, so I put a ceiling and kept going. And that did work. It was fine. I won't go through the rest of the details of the proof, but this is another thing which had to be formalized for the proof. The very last step, we run this algorithm. In fact, we run the algorithm twice. And what happens is that the proof works if there is no intersection between the red region and the blue region. This is something which comes out of the paper. You write down some quantities, you draw some graphs, and if these two blobs are disjoint, then the proof works.
What are these blocks?
These are essentially, as you go through the construction, if a certain inequality holds, then the proof goes through. If a different inequality holds, if a certain inequality holds, then the proof goes through, and that's the complement of the red. And if another inequality holds, which is the complement of the blue, then the proof goes through for a different reason. So we need that these two regions don't intersect or don't have any overlap for the entire proof to go through. So one of these alternatives works. And these are some specific explicit equations which are in the papers, and I don't want to slow on the slides because they're not that interesting. But this is something which needs to be formalized for the proof. And you can kind of see the scales of these things. The second one is a zoomed in picture of the first one, where I've zoomed into this slice where it does look like they intersect, but they actually don't. And you can kind of tell the precision that's needed to make this work. If you can't see the back, this is 0.72, this is 0.88, this is 0.38, this is 0.5. There's a fairly tight margin between these blobs. Another thing which you may notice about this is a fairly small detail, but there is a little there's a little jump there. That's not a rendering error. That's part of the equation. That's something which needs to be part of the proof and is actually vital for the proof working. And so this is also something that needs to be formalized. So how did the formal proof go? I needed to define edge labelings. These weren't in MATLAB. I needed to define Ramsey numbers. These weren't in MATLAB. Then there's a bunch of standard probability calculations, a bunch of counting arguments, a bunch of real and asymptotic analysis, similar to the ones I showed in the unit fractions project, and also some interval arithmetic, and as you see, in some tight numerical estimates that are needed. There's also some probabilistic constructions. I mentioned this lower bound of Erdős. There are some things similar to that, some standard combinatorial lower bounds for Erdős numbers, for Ramsey numbers, sorry, and some refinements of Stirling, again, similar to the ones I showed earlier. Along the way, here are some of the things I did. In particular, this is some of the most painful, some of the worst things which I had to do as part of this project. The first one actually is not that bad. This is kind of nice. This is a version of Stirling's approximation which holds for all n. Usually you say for like asymptotically large n, but this is a version which holds for all n. So this is an explicit upper and lower bound, which works for any n of this central binomial coefficient. Another one is that for sufficiently small positive epsilon, 1 minus the square root of epsilon is more than or equal to 1 plus epsilon to the power of minus floor of 2 times square root epsilon. If you stare at this a bit, it doesn't seem clear why this is true. It doesn't seem clear that this is true. And even worse, it doesn't seem clear how to prove it. So I came across this in the paper. I drew a graph and convinced myself it was true, and then eventually proved it. And I thought, that was painful. It would be nice if we had some automation for this. But hopefully this is the last one. Hopefully I only have to do this once, and I know how to do it if it happens one more time. And then it happened again, and then it happened again, and it ended up happening about 30 more times. And each one I thought, this is the last one. It was never the last one. I believe in Isabel, the real asymptotic should also be able to handle this, but in Lean we don't have that, so this was one of the more painful parts of the proof. Another one is this kind of explicit derivative calculation. We have some automation to handle things like this, but when there are more tricky denominators or side conditions, the Lean automation is not great at actually computing derivatives. This h here is the binary entropy function, so h of p will be minus p log p minus 1 minus p of log 1 minus p. In particular, when I have this quantity over here, this will not be differentiable at 2, like at x equals 2. So you need to do some special casing for that, and the existing Lean automation doesn't handle that nicely. So that was a bit painful. And then on top of that, I had to prove this inequality. For all x in this interval between 3/4 and 1, that not very pleasant thing is less than 1.9993. In particular, it's important that it's strictly less than 2. And you were asking earlier about the epsilon you get. The value of this quantity directly impacts the epsilon which you get. The true value is like 1.99929 or something like this. But I want to get it as, if I change this to a 1.9999, it would have been easier to do, but I want to get a good epsilon by the end. So that's why the 3 came up. And again, we don't have automation to do this in Lean. I ended up making some ad hoc interval arithmetic things to get this to work. There are other people who are doing more robust and more general ways of doing this, but they didn't exist at the time. One of the things I had to do related to this, we have these logs and log inside h. So I had to verify the value of log 5 to 23 decimal places. Same for like log 2, log 3, stuff like this. A bunch of these explicit log calculations. And this is not so bad with 5, but then there's also some worse logs to calculate as well. That's log 2 of 0.4339, I'm not going to read it out, and it has to be within this interval. That's a tight interval, and it has to be that to get this bound here. And again, we have no automation in Lean for this, so this had to be done as part of this proof. And there were 2 of these. Luckily, I had the foresight this time to do it in a slightly more general way to make it work for the other case too. Okay. So all that was done in 5 months, and it all worked. By the end of this, we have these 2 theorems. The first one says that for all sufficiently large k, the Ramsey number of kk is less than or equal to 3.999 to the k. So here I do have an explicit epsilon. Or I could do something which works for all k, and say that there exists an epsilon for which the same thing holds. And the paper is, as far as I know, still in the refereeing process. Okay. The informal paper, that's correct. This has also been done by Larry Paulson and Isabel, with a very nice paper. In particular, I enjoyed the discussion of the automation which you have in Isabel, and I felt very jealous about that.
Still took me twice as long.
Okay, let me talk about my last example now. This is related to the ABC conjecture. In particular, we're going to look at the set of exceptions to the ABC conjecture. I will say that the triple ABC is an ABC exception at epsilon if the triple ABC are pairwise coprime positive. So they're all positive and they're pairwise coprime with each other. and we have a plus b equals c, and the radical of a plus b, so this is the product of all the prime factors, is less than c to the 1 minus epsilon. The ABC conjecture famously asks, for every positive epsilon, are there finitely many ABC exceptions at epsilon? So if we fix epsilon, are there finitely many triples with this property? The full ABC conjecture is kind of difficult, so we're going to ask a slightly weakened version of it. We're going to look at the number of ABC exceptions at epsilon which are within a certain box. So I'm going to draw this box from 1 on 1 up to xxx inside this triple. And I'm going to ask how many exceptions are there to the ABC conjecture within that box, and see what this function does for large x. Trivially, this is bounded by big O of n squared. Very trivially, it's bounded by x cubed, because I'm inside a box of size x cubed. Slightly less trivially, you can bound it by n squared, because we have this a plus b equals c property.
X squared?
Sorry, x squared, thank you. Yes, this should be big O of x squared, because we have this a plus b equals c property. And the ABC conjecture is equivalent to saying it's big O of 1 instead. In October 2024, Browning, Lichtman, who's over there, and Teravainen showed n epsilon of x is bounded by big O of x to the 0.66. Now, I mentioned this analytic number theory class I took here in Cambridge. Another person in that class was Jared, and that's where we first met. Since then, since I did my master's here, we didn't stay in touch, but then we got in touch again for this project. That's another personal connection, which is something I like about this. And again, you can't see on the slides, but if you go to URL, you can see the preprints. What's the idea of this proof? The equation in a plus b equals c with this radical, it's an equation in 3 variables, and we want to see how many solutions there are. But it has this radical thing, so I'm going to try to reduce it into Diophantine polynomial equations in many variables. So we're going to go from a single equation in 3 variables into many Diophantine polynomial equations in many variables. We're then going to bound the number of solutions to these polynomial equations in 4 different ways. So now I have this system of Diophantine equations. I'm going to try to bound the number of solutions they have, and that will give me some idea of how many solutions the original thing had. What are these 4 different ways? The first one is Fourier analysis, the second one is geometry of numbers, the next one is the determinant method of Heath-Brown, and the last one will be counting solutions to 2-way equations. These are from fairly different areas of maths. They're not entirely related to each other. And so describing these are 4 different techniques we're using for the same problem. But once we have these collections of bounds, it turns out we can combine these. And together, these give you a contradiction unless this n epsilon of x is smaller than x to the 0.66. Another thing I should mention, the 0.66 is an interesting number. You might wonder, this seems kind of close to 2/3. And in 1962, de Bruijn, the same one who we've heard about earlier, showed n epsilon of x is big O of x to the 2/3. So this is 2/3 opposed to 0.66, and remember the trivial bound was squared instead. Okay. So I wanted to try to formalize this, or we wanted to try to formalize this paper. In particular, the first thing which we wanted to do was this last bullet point here, combining these numerical calculations. Why did we want to formalize that part first? Well, the 4 things listed here, these were known before the new paper. Some of these were known since like the 80s or 90s, and taking Kevin's lead, we thought let's try and do the new stuff first and fill in all the gaps later. It's kind of Kevin's standard of proof, well, FLC standard, let's say. So we tried to go for that first. And then we also tried to do 1 and 4, and 2 we haven't thought about much just yet. But now the project is open, so if you are interested in contributing, that could be fun. So how did this go? Section 4 we did first. This was in December 2024. This was largely me. This is essentially all the numeric calculations. It took about 1,600 lines of code. I was talking to Jared afterwards, and he told me he was personally worried for about a month about these. He delayed the release of the paper to spend a month checking that everything in here was correct. And he was significantly relieved, is the direct quote, that Lean accepted it. And he also told me that the reason he got into the Lean community, or decided to join formalization in general, was specifically to verify section 4, because that's the part he was unsure about. So that's the part which I did first. And then Aaron, who is sitting over there, also joined the project. And then we did section 2.lean. So this was the first bullet point from the slide I had before. This is the step which reduces the ABC problem to a problem about diaphragm integrations. So this was largely his work. Reducing it to this diaphragm equation, and it's about the same number of lines of code as the earlier part. And then I mentioned that we also wanted to formalize this de Bruijn bound, and so that's in de Bruijn bound.lean. This was earlier this month. It's about 3,700 lines of code. Okay, so that's essentially all of the things I wanted to say. So actually, I should show you the file first. I would like to show you this main file and convince you of what we did. So this is my actual lean code. Let me make it a little bit bigger. So I've imported those 3 files. I have some lemmas making sure everything lines up, and then we have this demo. Okay, so I have this ABC exception set, which is the set I gave you earlier, and I have a proof that a triple ABC is in this set if and only if each of the 3 is positive. They are pairwise coprime. We have A plus B equals C, and the radical of A times B times C to the 1 plus epsilon is less than C. You notice the epsilon has gone on the other side. It turns out this is just more convenient. This radical is something in lean already. This has been there for quite a while. And then we have the exceptions to the ABC conjecture, which are inside a particular box. That's what this second theorem is saying. And so I have this definition, which is the number of exceptions within this box bounded by x, sorry. And here again, we have 3 coprime integers, which are within this cube from 1 up to x. And this time it's more convenient to put epsilon on the other side. So I should be clearer. This epsilon's on this side because that's the usual formulation. Like if you go on Wikipedia, let's get rid of that. If you go on Wikipedia, it will have the epsilon on the left-hand side. And for the paper, it's just more convenient to put the epsilon on the right-hand side with a minus sign. And I will show you in a moment that you can basically do this and doesn't change the truth of the conjecture.
So the sets are exact. Oh, the 2 different sets.
They're 2 different sets. The second one has this restriction that it's upper bounded inside the cube. So the second one is definitionally finite. The first one is conjecturally finite. And there's also this slightly subtle difference of the epsilon. And I'll convince you in a moment that, or I'll show you that I've convinced Lean that that doesn't make a difference, but I want to show you both of these so you can see this is the one we actually use, and this is the one that's on Wikipedia. They genuinely are the same thing. And then we have this count triples function, which I denoted by n sub epsilon earlier, which is just the size of this set, the size of the exceptions within this box. Then the ABC conjecture by definition is that this first set is finite for every epsilon. And we have these equivalences. So the ABC conjecture is equivalent to the statement that for all sufficiently small epsilon, small positive epsilon, this n epsilon function is bigger of 1. That's the equivalence I claimed earlier, where I can relate this size of this box to the ABC conjecture itself, and that's accepted by Lean. And then we have this de Bruijn bound, which is that for all sufficiently small epsilon, in fact I just can give an epsilon of 1 over 100, that is bounded by n to the 2/3. And this one has been, Lean is happy with this. And then the one which we are still working on, which is why it's sorried, is a bound of 0.66. Here we have epsilon being quite a bit smaller. It only really matters for sufficiently small, but I've made it precise anyway. And this is the thing we're currently working on. Okay, and just to be doubly sure, I also ran this through Lean 4 Checker, and Lean 4 Checker is also happy with these proofs. Okay, great. Let me go back to my slides. So, in conclusion, very recent combinatorics and analytic number theory and order theory is immediately accessible to formalize quickly. It's doable for, I would say, a large portion of modern combinatorics results, not just special cases which have a lot of attention. I would estimate that maybe about 10% of the things on the archive in combinatorics is something that could just be formalized. It could be doable by one person. It may take a bit of time, but there's no real obstruction to getting it done. Essentially, MathLib has everything needed to just get this done in Lean. One factor about this, which you've kind of seen from the earlier things, especially from Fishbone, is that these proofs don't often have many prerequisites. Specifically, the kind of depth and difficulty and complexity of combinatorics is conceptual rather than contained in the lemmas. And you saw this earlier from the book algorithm compared to the algorithm from the 30s, where the idea was something which evolved, but not necessarily in that case it was also the proof, but typically it's usually just the ideas which change over time. And these proofs often have very concrete aspects, so I have to prove these very explicit calculational things, which is tricky and awkward, but it is doable. So this is almost everything I wanted to say. But there is one gap which I had. There's one fairly glaring gap. So hold on a second. I said that I did the first part, and I and Aaron, but mostly Aaron did the second part. Who did this third part? Neither. Trinity. What is Trinity? I will now pass over to Jared.
Well, so I'd like to thank first off Bhavik for setting my mind at ease about being able to write confidently this result that the exceptional set is big O of x to the 0.66, and as he explained,
Write it on the center board because that's simple.
okay,
Let's move it up in a second, I think.
yeah, I will. But I personally was quite anxious about this result, and I was going informally, manually by hand through the lines to be confident enough, and I was really kind of breathed a sigh of relief and thank the Lean community, especially Bhavik, for being able to be confident in this result. And recently, Bhavik and I, we've announced a GitHub repository to a kind of big proof initiative to actually formalize the entirety self-contained result, including all the references, very down below in the valleys. We're confident about the peak in Kevin's analogy of the very top, but we really want to fill out and have a self-contained proof. And maybe just kind of context for this previous result. So De Bruyn, or De Bruyn, depending on how you pronounce it, appeared many times in this conference. He proved kind of the first result of this kind, that the exceptional set is big O of x to the 2/3. And as Bhavik mentioned, the trivial bound is x squared. So in a box, in a cube, you expect x squared many points where a plus b equals c. And this gives a quantitative form. De Bruyn showed that the ABC conjecture is true almost always, for almost all equations. And I could stop there, but being at this conference, I think it's natural to mention that this result has now been formalized. Not just to Kevin's standard, but completely self-contained with no dependencies. Yeah, so here is kind of a quick blueprint. This is now available on GitHub, and as well as the over 3,500 lines of code. You can scroll down quickly.
So this is longer than the proof of the other one.
Exactly. And moreover, this result was auto-formalized. So today we're announcing a prototype of the Trinity auto-formalization agent, which produced over 3,500 lines of code, 100% on its own. And this initiative is part of Christian Zegedy's verified superintelligence program developed with Morph Labs. And the GitHub with all these lines of code and the corresponding blueprint is available. So maybe in just a brief minute or so to kind of explain what went into this kind of pipeline. So we start with just the archive paper of De Bruyn's theorem, expand that out in the kind of standard protocol, as you guys have been using, of creating an informal LaTeX document of all of the precise lemmas.
But manually.
Manually, this is what I did. I did the manual labor as a guinea pig, and I provided just the, essentially, kind of in words, the dependency graphs of the previous lemmas that are being depended on. And based on that taken as input, we fed it to the early prototype of the Trinity auto-formalization agent. The first thing it did was combine informal proof attempts of these statements, supplied them into its context, and then proceeds to formalize each of the constituent statements and definitions on its own, iterating many times, diagnosing its own issues as they go, with various errors getting fed to it. Once, on most occasions, the vast majority of the statements would be formalized completely okay. Sometimes it would need to retry more for a few kind of more difficult lemmas. But eventually, after syntactically compiling all statements, all we did was kind of kind of semantically verify that the final statement and the definitions used therein were corresponding to the results we wanted. And also kind of Bhavik was able to kind of double check with us. And once we were happy with these statements, we were able to feed it back into the Trinity agent, who was then proceeding to take these statements and informal proofs and convert them into formal lean and iterate. In many occasions, it was able to formalize just straight shot after iterating on its own, diagnosing its own issues. There were some lemmas that it was struggling even after many attempts, and after a certain time counter got reached, it would then start to instead try to decompose into these difficult lemmas into sub-lemmas, which it would then propose these decompositions, which would then be kind of human spot checked if they were kind of relevant, if they were going anywhere. And we kind of iterate this process several times over and over. And so this is a very early prototype. So we began this project only in the past month, and a lot of the lean was developed in the past 2 weeks. But as we scale up this initiative, we're really hoping to accelerate, for example, from Formalising theorem, also all these big proof, large-scale initiatives that would otherwise take quite a long time. And in the coming months, we're aiming to release open source tools for the community to be able to use and to contribute to the working mathematician.
Thank you.
Well, that's totally awesome. Right, questions?
Yes.
You mentioned the problems with computing with real numbers. So this should have been trivial in either Rock or Isabel. Manuel mentioned the impressive work by Fabian Imler, for example. So what's the current status? So you could do two things, either interval analysis or exactial analysis. What's the current status of these libraries?
What I did was interval analysis, where you bound by rational numbers. There are other projects which are independent of mine, which either have computable real numbers or other forms of interval arithmetic. Those are different from what I did. What I did was just the most rudimentary interval arithmetic you can think of. I believe what Rock and Isabel have are both individually superior to what Link currently has. Yeah.
Two questions. I guess number one, could we go back to the slide with the URL?
Yeah. That one?
Yes, thanks.
Yep.
And leave that up because I'm going to ask my other question. And then
Sure.
right up the URL.
Okay.
So I was wondering, kind of what are, I mean, it's very cool that you're doing this work so quickly to the original proof generation, but I'm wondering sort of what are the incentives for you for doing it? So in particular, like, are you publishing papers about these formalizations, or how do you give any comments you like?
Yeah. So my main motivation for this is twofold. Firstly, because these formalization methods were often pitched as being useful for, or trying to be useful for mathematicians at the moment, but all the things that were currently being done was, in my impression, quite far from what mathematicians were currently doing. And so what I aimed to do was bridge the gap, or at least show that in some places the gap was surprisingly small. The other thing was because I wanted to demonstrate to other mathematicians that proof assistants can do things which are relevant to them. I think for mathematicians outside of formalization communities, they often only get interested when they see a result which has been formalized that they personally care about. And I think I mentioned before that I was mostly in the category theory community, but I was also involved a bit in combinatorics, and so I wanted to capture that community, and I realized that, especially in that area, it was fairly feasible to do. So that's why I picked these results, because they were, in some sense, high profile and difficult. And then the third motivation is just because I wanted to understand these proofs. I thought these were cool proofs by interesting people and interesting ideas, and by formalizing something, you are kind of forced to understand it very well, and that's something which I wanted to make myself do.
Right, so sorry, I just want to follow up. I mean, you know, those are great answers from the point of view of the scientific motivation for this, and 100% endorse everything you just said. But
Okay.
I meant the question also in the sense of like career incentives.
Mhm.
I mean, it's, you know, it seems like, you know, you're able to do these, you know, difficult formalizations at a relatively economical time scale. That's something that demands a lot of expertise. Do you feel like your expertise is being recognized, rewarded, that sort of thing? I mean, so this might not be a concern of yours, and I don't mean to make it a concern of yours, but I've heard a concern expressed by other people that you know, time spent on formalization might not be credited in the same sense as, you know, the credits given to the authors who wrote the papers that are still in the refereeing process, for instance.
This isn't something I have a large concern about, but it is something I sometimes think about. I sometimes write papers, and I should write more papers. Many people have told me this. I think I'll need to think a bit more to give a more coherent answer to this. It's a good question. Yeah.
Jared, how much did it cost and how long did it take?
I don't know. I mean,
Nobody ever bloody knows. Nobody ever tells us.
I mean, one of the aspects is that I didn't really. Oh,
Maybe other people in the room know.
but I mean, I was just going to say that from my perspective, the extent of my lean experience is essentially using, you know, like the natural numbers game. So, you know, you know, I don't really speak to, you know, the lines of lean code, but I think maybe Jesse knows more about the.
Jesse, can you say more about how long it took and how much compute was used?
So from beginning to end, we've been at this for about a month, but work on the agent has really only been in full swing for the past couple of weeks. It's still a very early research prototype. We did partner with Lambda Labs to bring online a training and inference cluster for this, but we're not ready to disclose precise details, although there will be a white paper, and most, if not all of this, will be open sourced in the coming months.
Maybe you can have like a rough number. If I were to run this like privately, how much would it?
Not that much.
How much you live in Switzerland?
No, your money
Cheaper than paying. Is it cheaper than paying him to do it manually?
Yes.
So,
Okay.
you know, in 1975 or so, Boyer and Moore made a system where you could type in a series of conjectures, very simple conjectures on things like factorizing numbers uniquely into primes, and it would automatically give proofs just in kind of mathematical English. So here is kind of zoomed up many orders of magnitude, where you're actually generating a formal document and obviously much more difficult material, but it is somehow a continuation of the same idea 50 years later.
Yeah.
Of course, you have a much more powerful computer than they did.
Yeah.
Is this a scientific thing, this Trinity? So was the blueprint written just once by a human and then auto-formalized, or was it modified by a human to try and get to one that was auto-formalizable?
My understanding is that it was written by a human, then a formalization attempt was run. If after many attempts there were parts which couldn't be proved, that part of the blueprint was expanded.
Expanded by a human.
Yes. But I think it's important to mention, I'll come back to the slide in a second, but this blueprint tech file It's a lot like the blueprint of any other project, but it doesn't contain proofs. That's important to say. It contains statements, and it contains the dependency, so we have all the edges, but these nodes don't really have that much information other than the statements. So when it was decomposed, it was a decomposition of statements rather than of proofs. Yeah.
So there's been quite a bit of work on formalization of combinatorics, I mean, from decades ago, because it's used for termination of rewrite systems.
Yes.
I mean, Grosvenor basis and so on. Is your work relevant there, or will your techniques be reused to prove that algorithms terminate in Lean?
I had never done it with that intention, and so I don't know that it will be directly relevant to that, but I think some of the ideas in some of these proofs may be relevant for that. In particular, so this algorithm I mentioned, it's important to know that it terminates, and this is kind of the other way around of I'm using termination measures to show that my proof makes sense. But I could also imagine it happening the other way around, where an algorithm only terminates because of some mathematical fact. I believe it could be useful for that, but I haven't looked for or seen any explicit examples of that. Yeah?
So looking at the code that was produced, it's
Yes.
very pretty. Like it not only works, but it's like nicely formatted, line lengths look good, they use
The line lengths do not look good.
Okay,
Sure.
I think it also makes comments, but sometimes those comments are not like not relevant.
It still looks, I haven't looked
It's
much
not bad.
but it looks much nicer than most of the AI-generated proofs I've seen. Did you train it to produce nice proofs? Like, is there a value function there how did you get it to do it?
I think that's a question for Jesse.
Well, I mean, outputting code interleaved with comments, I think, is very standard in post-training mixtures these days. I wouldn't trust the surface appearance of the code. If you actually run it, it's like very non-standard. Like a lot of warnings due to like non-idiomatic.
But even the fact of calc chains, like I would expect a calc chain, it doesn't really add anything to the correctness of the proof, and once you have the proof, you could make it, you don't need the calc chain, you just write transitivity or something. It really just makes, the only benefit of a calc chain seems to be to make the code readable. So it seems that there must be some motivation for the AI to produce readable proofs rather than just correct proofs or short proofs.
Oh yeah, I think if properly trained, systems like this will actually produce much more readable artifacts than, say, the median formalization PhD student who's chained in a dungeon somewhere, forced to select symplems.
Did you have that student for comparison?
Yeah, there was a question at the front.
So, wondering, I mean, the proofs that you showed, you have to do these very delicate estimates, sometimes horrible long things. Auto-formalize things, I mean, does that happen? I mean, the original deep learning proof probably has something like that.
Not to the same extent. It has some kind of estimates, but not of the same sort of flavor as the horrible ones I showed. I think there are some simple ones, and there is some things automatically done in that direction, but they're not nearly quite as bad. And is it okay if I show the lean file? This is to your point about the line length. It's full of errors. You can see the yellow board, each one of them, sorry, full of warnings. Sorry, that's important. No errors, but full of warnings. 420 warnings, apparently. Lots of overly long lines, some deprecated lemmas. And I believe that it was generated using Lean 4.20, and the project is on Lean 4.21 RC3, I think. So there's also a difference there. It worked, it just happened to work on the same version, but there are deprecations, there are overly long lines. There are some, yeah. I also have the flexible linter tunnel on in my project because I'm that kind of person and it fails the flexible linter. There we are. Yeah.
So a couple of years ago, Zegeli was always saying, I don't want to learn anything about Lean because auto-formalization should be completely set up without learning anything, without anything specific to the proof assistant. So is this what happened in the end, or did you have to do anything specific?
You'll have to ask Jesse.
Yeah, I think I certainly can't speak for his true motivations. I could only say that my motivation for sticking with Lean as opposed to not going for something else is essentially what Alex said earlier, like his kind of ideas. And the impression I have is that many people like using Lean for this kind of mathematics, or for kind of automatic mathematics, for reasons that Alex described. I can't speak for someone else's motivation, but that's my...
Yeah, but I don't mean, I didn't mean the question as should we use Lean or something else. He was saying we should not learn anything about the syntax on Lean, just the LLM should just spit out Lean files and this will work and without anything specific to the program, to the proof assistant. So in the pipeline, are there Lean specific tools, or is it simply manipulating strings and outputting strings after?
It's using a modified pantograph server and actually spawning hundreds of them per theorem proving attempt. And so it has access to the ability to create new goals, to like run the Lean verifier, like do a compiler check on proofs which it submits. But it's actually very, very general. But the intention is for the human to not have to worry about the details of the implementation, but to rather use the informal blueprint LaTeX file as sort of a control plane for directing these swarms of auto-formalization agents.
Okay, but the use of pantograph is not what was the announced goal in the beginning. No, that's good. That's interesting.
Yeah.
And can relieve.
Yeah, maybe on top of that, it's worth mentioning that I only saw this file after the entire thing was finished. So in terms of checking that the statements made sense, except for the very last one and the definitions, I never saw any of the intermediate statements. That was like Jared checking it and he can't write Lean. So
but you've run everything through some verify.
Yes, I've run this all, like after they sent this complete file to me, I ran it through Lean and then I ran it through Lean 4 Checker. And then I read it. Yeah.
Are you kind of sad that some of the tasks you were doing, you said are fun, are now automatable?
There are many tasks in the world.
Find other ones.
Exactly.
Harder ones.
Right.
I think one more question, and we're way over time, of course, this is the last talk of the day, so it doesn't matter, but sure.
I'll make it very short. So how much shorter would this file be if you used Lean Hammer?
Oh, that's a good question. I'm not sure, I haven't tried. What I can say is that I think I could get this file down to less than 1,000 lines. There are lots of things in here which are not necessary. So Jared split up the blueprint into separate parts. He didn't know what Lean already had. So some of the parts were things which did not need to be, so I can show you an explicit example of this. I don't mean to insult you. One of the theorems which he wrote down was the fundamental theorem of arithmetic. And so the agent stated this theorem and found the instance for it, but then this never got used. Because whenever you need to do this, Lean would just do instance search and find the thing already. So this is a small example of something which could just be removed. And there are many others. So this one, I think I tried to find a shorter proof. I got it down to like 5 lines or something, and it's quite a bit longer. So human inspection can get these quite a bit shorter without much automation, and with automation, I imagine it could be even shorter. Matt, did you have a question?
Yeah, I was just curious if you drop it into some setting where there's not a lot of foundational material, like PDEs, right? How much is the success here dependent on a certain amount of knowledge within already of the mathematics, of the basic mathematics?
That's a fair point. Was it theorem 33 that was the last one?
Yeah.
Okay.
That one was responsible, I think, for the 1,000 lines of code on its own.
So I think it's this theorem. This one here. This single lemma. Maybe I should show it.
So it says that the product of k different series equals the k-fold sum of products. This one. So it's like interchanging sums and products.
Okay. This one is responsible for 1,000 lines out of the over 3,000 line file. This one...
Just expand it out, right?
Expand it out, but also it's essentially in Mathlib. A statement which is basically this one, up to 2 or 3 lines manipulation, is in Mathlib. The reason I mention this example is that this was a 1,000-line proof found by this agent for something which Mathlib did know, but seemingly the agent didn't know that Mathlib knew. So this is kind of an example of, this is the closest thing I know of mimicking what would happen if we were in a domain that math didn't know anything about. In this case, math did, but the agent didn't know that. So this is the closest approximation I have to how that would look. In that it's possible, but also this is not particularly sophisticated. Yeah?
Let me make something more precise.
Okay.
I searched for structure in the file.
Okay.
Keyword structure.
Yep.
Find a keyword structure.
Okay.
I assume I won't find inductive.
I expect not.
But that'd be great to, like,
yeah.
That would be, yeah.
Yeah, that's true. It would be amazing. Maybe to that point, it's worth saying this is the first attempt. This was genuinely the first thing that was tried to be formalized. I think this got started about 2 weeks ago. This is the very first attempt, just because we were trying to formalize this separately without AI since around December, and this was just genuinely the first thing we tried. I would also like to see how it behaves on other sorts of math, other areas of maths, other styles of formalization. It's a great question.
Shall we release everyone who wants to go, and people who want to continue to ask questions can stay? How about that? So, yeah.